Welcome back to Fundamentals of DC Circuits. In this video, we're going to discuss series parallel circuits. The learning objectives for this video are that you will be able to analyze a series parallel circuit. We're also going to learn how to analyze a loaded voltage divider, as well as a ladder network and a Wheatstone bridge. So today we're going to put together all of the tools we've been discussing so far. In order to solve or to analyze a series parallel circuit, which is a combination of things in series and things in parallel, you have to be able to combine the ideas of Ohm's Law, KVL, KCL, voltage divider, current divider, as well as understand the fundamental principles behind resistors in series and resistors in parallel. So today, what we're going to do is explain how we apply all of these techniques to solve a circuit like the one on the right. Notice that we've got a resistor here that's in series with the voltage source, but then the current through R1 is going to split. Some will go through R2, some will go through R3. That current is going to come back together right here and then split again. How do we solve a circuit like this? How do we find the current and the voltage for every resistor in this circuit? You're only going to be able to do that by applying the techniques that we've been discussing in previous videos. And today we'll look at some examples of how we do that. So here's our first series parallel circuit. What we're going to do is determine the voltage drop across each resistor in the circuit below. And we're also going to figure out the value of the source voltage. So, to begin, we're going to look at what we're given. In this case, we have a source voltage that is unknown. We do know the total current. We know that the total current has to split. Some will go through R1 and some will go through R2. That total current will recombine right here, which means we know the total current going this way. It's 1 milliamp. It'll split and recombine. Then that 1 milliamp will split again. Some will go this way, and some will go this way. R4 and R5 are in series, which means they have to have the same current. R1 and R2 are in parallel, which means they have to have the same voltage. So let's begin attacking this problem. Remember, the goal is to find the voltage drop for every resistor, R1, R2, R3, R4, and R5. First step, we're going to perform a current divider on R1 and R2. We know the total current going into this node. We're going to figure out how much current goes through R1 and how much goes through R2. If I know the current going through R1 and the current going through R2, I can use Ohm's Law to find the voltage across each one of those. So that's going to be our first step. In order to perform that current divider, I have to take the total resistance of the two paths where current splits. Keep in mind, I'm not finding the total resistance of the entire circuit. What's important is this 1 milliamp split. Some went this way, some went this way. So I need to know the total resistance of just those two paths because these are the only two paths where the current splits. It comes back together right here. So we're not worried about these resistances. We're only worried about the total resistance of the parallel paths where the current split for this piece of the problem. There's your total resistance. Now I can set up my general current divider formula to find the current through R1 and the current through R2. Keep in mind, if I add these two values up, I get something really close to 1 milliamp. Now that I know the current through R1 and the current through R2, I can simply use Ohm's Law to find the voltage for R1 and the voltage for R2. So there's my currents that we just calculated for R1 and R2. Use Ohm's Law to find the voltage for R1 and the voltage for R2. You'll notice that you get the exact same number. Since R1 and R2 are in parallel, this makes sense. You should get the same voltage for both of those resistors. Now we're going to perform a current divider on the second half of the circuit to also find the current through R3, the current through R4, and the current through R5. So we're going to repeat the same process that we just did, except now we're analyzing this piece of the circuit. We know that 1 milliamps has to come out of here and then it splits. So the first thing we have to do is find the total resistance of these two paths. Keep in mind we have two paths, this path and this path. These resistors are in series, which means I'm going to combine them together. And then I'm going to take the reciprocal of that number plus the reciprocal of 3.9K, add that up, take the reciprocal of that to get my RT. Then I can set up the general current divider formula to find the current through R3, your total resistance divided by R3 times the total current coming into this node. And the current for R4. Keep in mind the current for R4 is also the current for R5. That should say R5. Now I know the current for R3, R4, and R5, and I'm going to use that and Ohm's Law to find the voltage for R3, R4, and R5. So we know the current for R3, we know the current for R4 and R5. Use Ohm's Law to find the voltage for each resistor. Here's the voltage for R3. Here's the voltage for R4. Here's the voltage for R5. Keep in mind that R4 and R5 combined are in parallel with R3. Therefore, if I combine the voltages for R4 and R5, it should be equal to the same voltage you got for R3. And we can see that if we add these two up, you'll get something very, very, very close to 1.35. So at this point, we have found the voltage for all 5 resistors. We've answered the first question. The next question is, what is the value of the source voltage? We're going to use KVL to find this. There are a number of ways you could find this. This is just one option. KVL is one thing you can do. Here's how you would do it. First of all, I'm going to add to my diagram the voltage drops for R2 and R3, because this right here forms a closed loop. If I sum the voltages around a closed loop, I can use KVL to find the missing voltage Vs. So if I start here on my loop and go clockwise, I'm going to have plus 0.688 volts, plus 1.35 volts, minus Vs equals 0. I can solve that for Vs to get 2.038 volts. So it's approximately a 2-volt source. Keep in mind, this is a closed loop, and this is also a closed loop. So when you're looking for closed loops, these are different ways you might be able to identify them. So our next problem is a little bit more complex. Notice that we have more of a triangle orientation here, and we're going to do the same thing that we did in the first problem. Determine the voltage drop across each resistor and find the voltage VAD. So what you'll see on the screen is how we're going to first start by finding the total resistance in this circuit. First, we're going to start with something I call Rx. Rx is going to be the combination of this resistor and these two resistors. This path is in parallel with this path. These two resistors are in series, so you're going to combine them. Once you combine them, you have two paths, the 10K path and the combination of these two. Those two paths are in parallel because current will start here, split here, and then come back together right here. So these two paths are in parallel. I'm going to calculate the equivalent resistance of those two parallel paths using the formula described in the previous lecture slides or lecture video. And you're going to combine these together to get 5.07K. So these three resistors combine together to form a resistance of 5.07K. Now I'm going to do Ry, which is the bottom half of the circuit. The current that split and recombined right here splits again. Here's one path, here's another path. These two paths are also in parallel because current splits here, comes back together at the end. These two resistors are in series, so you're just going to combine them together and then find your parallel resistance. So in this case, Ry comes out to be 947.37 ohms. Rx was the top half of the circuit. Ry was the bottom. Rx and Ry are simply two groups of resistors that are in series. Once you collapse all of these things down and you collapse all of these things down, what's left is just Rx right in series with Ry. So your total resistance comes out to be the sum of Rx and Ry, 6.02 kiloohms. That was our step one. So our next step is to find the total current. The total current can be found by taking the total voltage divided by the total resistance we just found. So this number, 16.61 milliamps, represents the total current that leaves the voltage source and goes into node A. At node A, it will split. Some will go this way and some will go that way. So the next thing that we're going to do is use a current divider to figure out how much current took each path. So we're going to use a current divider to find the current for the 10K, the 4.7K, and the 5.6K resistor. In order to do that, remember the first thing you need is the total total resistance of your two paths. We already found that total resistance. That total resistance is Rx. We've already found it. So we can use Rx to set up a current divider. The current through the 10K resistor has to be the total resistance of both paths divided by 10K multiplied by the total current coming into this node. So here's how we'll fill in that equation and solve that for the current through the 10K resistor. The 4.7K and the 5.6K are in series. They have the same current. When we set up our current divider formula, the total resistance will go on top, and on the bottom will be the total resistance of this path. That's why you see these combined. We want the current through this branch, and there are two resistances on that branch. So the bottom of your fraction has to be a combination of both of these resistances. Then you're going to multiply by IT and get that the current through the 4.7K and the 5.6K resistor is 8.18 milliamps. Again, use KCL, add these up, and make sure you get what you started with, which you do. Now we can use the currents from the previous step to find the resistor voltages for the 10K, the 4.7K, and the 5.6K. You're just going to use Ohm's Law. So you're going to have V equals I times R. Take the current through each resistor multiplied by its resistor value. Since this branch is in parallel with this branch, this voltage should be equal to the sum of these two voltages. And we can see that it is. If you add 38.45 and 45.81, you'll get something very, very close to 84.2. Now I'm going to label the diagram with the voltages that we just calculated. Remember, polarity is important. Plus is where current enters, the minus is where current exits. Next, we're going to use a current divider to find the current through the bottom half of the circuit. We're basically repeating the same process as before. The current that is right here is the total current because it is split and recombined at this point. Then it'll split again. So we're going to use a current divider again, and in order to do that, the first thing we need is the total resistance of our two paths. We've already found that. That's Ry. Next, you can set up your current divider equation by plugging in Ry in the top and then the value of the resistance for the branch on the bottom. The 1Ks are in series with each other, so they'll have to have the same current. Your current divider has to have Ry on the top, that's your total resistance of these two paths, divided by the total resistance of the branch. In this case, I have two resistors along this branch, so I have to combine them when I plug them into my current divider formula. The last step is to use the currents from step 5 to find the corresponding resistor voltages. So the voltage for the 1.8K comes out to be 15.73 volts. Remember, you're just using Ohm's Law here. You're taking the current through that resistor. We just found that current, multiplying by its resistance value. Do the same process for the 1K. Make sure you're doing the current through that resistor, which is 7.87 milliamps, times the value of its resistance. Lastly, I'm going to add these voltages to my diagram showing the proper polarity. Remember, current flows through here, recombines here, and then flows out this way and down and around this way. So my polarities are showing that, with the positive side showing where current enters and the negative side showing where current exits. So now we've answered the first question. We've determined the voltage drop across each resistor. Lastly, we need to find the voltage for from point A to point D. So from here to here, we're going to find the voltage. In order to do that, we're simply going to sum each voltage that we encounter using the polarities we've labeled to figure out the voltage from point A to point D. Here's what that'll look like. If I go this way, I'm going to have a positive 38.45 volts, a positive 45.81 volts, and a positive 7.87 volts. If I add all those up, I get 92.13 volts, which represents the voltage from point A to point D. Next, we're going to move on to a new concept called voltage dividers with a resistive load. At times, you'll have a load resistor called RL that may be connected to a voltage divider from the output to ground. This load resistor is in parallel with R2 and will reduce the output voltage by a certain amount depending on the value of RL. We have two pictures at the bottom. The first is what we call an unloaded voltage divider, meaning there is no load, there's nothing connected here. And then with a loaded voltage divider, there's a resistor connected here. And we measure the output across RL. If there is no load and it's unloaded, we're measuring the output right here, and basically we're just measuring it across R2 because there is no RL. So what we're going to do is determine the unloaded output voltage of the voltage divider below, and then find the loaded output voltage when you have RL with a value of 10 kiloohms and then with a value of 100 kiloohms. First, we're going to start by determining the unloaded output voltage, which would just be the voltage across R2 if we did not have a load at all. Say that there's nothing connected here. It's gone. Without a load, the voltage divider is composed of just R1 and R2. So you're going to set up your voltage divider formula, which would be R2 divided by R1 plus R2 times Vin. You get a voltage of 3.40 volts. If you have no load, that's the voltage you're going to measure across R2. That's your output voltage. If you were to add a load, you now have, let's say, a 10K load. And now you have a voltage divider with R2 in parallel with RL. So first, before I can do a voltage divider, I have to combine these. These are in parallel. So I'm going to combine these and call it Rx. Once I combine these, my circuit is now R1 in series with Rx, because these two will be replaced with the value of Rx. So now my total resistance in the circuit is R1 plus Rx. Now when I do my voltage divider, I'm going to do the voltage divider with Rx on top, which is these two combined together, divided by my total resistance times Vn. So by adding a load to the circuit, I decrease the output. Now the output is only 2.58 volts. If I were to repeat this with a 100K load, Rx would now become 9.1K. Again, if this load is increased to 100K, it's in parallel with R2. We have to combine these together. So we're going to combine them and get 9.1K. Next, the total resistance in this circuit is R1 plus this combination of Rx. And then we're going to set up a voltage divider. We're going to find the voltage from this point, which will be the voltage across this combination, that's Rx, divided by the total times Vn. Now our output voltage is 3.30 volts. So notice that by changing the load resistor, we can control the output voltage you see here. If I go back a few steps, the unloaded output voltage was 3.4 volts. If I add a small load of 10K, I decrease the output to 2.5 volts. If I add a large load of 100K, the output becomes 3.3 volts. So why is this important? Basically, let's say that in your lab, you set up a circuit like the one on the right, and you have two resistors that are in series, R1 and R2. They're both 470 kiloohms. But when you add the voltmeter so that you can measure the voltage across this resistor, you're only measuring 4.04 volts. Let's say that you have two voltmeters. This one is measuring the voltage for R1. This one is measuring the voltage for R2. This is a series circuit. So because of KVL, we know that the voltage for R1 plus the voltage for R2 should equal 10. But your voltmeters are telling you you're only getting about 8 volts. Well, what you've done is connected a load to your voltage divider. And each one of these instruments has its own resistance. So here's what's happening. All measurements affect the quantity of what is being measured. A voltmeter has its own internal resistance, which can change the resistance of a circuit. So this voltmeter, if it had a better internal resistance, would measure closer to 5 volts. In this case, these voltmeters have a 1 milliohm, this is supposed to be ohms, internal resistance. And a typical voltmeter generally has 10 megaohms or more. So when your voltmeter has a lower internal resistance, it can affect your measurements. And this is literally an example of what we just saw. When you have a loaded voltage divider, the voltage across your output can be affected by the value of the resistance of the load. In general, you want a very, very high resistance of your load so that your measurements won't be affected. Next, we're going to move on to another concept called ladder networks. A ladder network is a series parallel circuit. And what we're going to do is determine the current through each resistor and the voltage at each node with respect to ground in the ladder network below. If you take a look at this circuit, R1 is here, R2, R3, R4, R5, and R6. There's only one relationship you can work with here. R5 and R6 are in series. The rest of this circuit does not have anything in series or anything in parallel. For example, R3 is not in series with R4. They can't have the same current because current has to split here. Some will go through R4, some will go this way. R2 and R4 are not in parallel with each other because you have a resistor up here. R2 is not in parallel with the 45 volt source because you have a resistor here. So there's only one relationship you can work with, which is the fact that R5 and R6 are in series. With a ladder network, we generally start from the right, work our way to the left by collapsing things one at a time. And that's what we're going to do to attack this ladder network circuit. First step is to combine R5 and R6. They're in series, so I can add them together. I'm going to give this a new name. I'm going to call it RW. So these two resistors have now been replaced with RW. Now, our next step is that RW is now in parallel with R4. I'm going to make these two into a new combination, and I'm going to call it RX. Next, I can see that RX is in series with R3. I'm going to make a new combination. I'm going to call that RY, and I'm going to add R3 and RX together. Now I have this. RY is now in parallel with R2. So I'm going to make a new combination, call it RZ, and figure out these two in parallel. Finally, I'm down to just two resistors left, and I can say that the total resistance in my circuit is R1 plus RZ. That's the total resistance. So I've started from the right, worked my way to the left, collapsing two things at a time. They might be in series, they might be in parallel, but I've made one, make a collapse and give it a new name, give it a new label, and then as I have shown you a new picture with each step, you should also redraw your circuit with each step so that you can see how you collapsed it. And you may have to go back to one of those intermediate steps to find a value later on. So now that I know the total resistance, I can find the total current. And I also know that the total current has to be the current through R1 because R1 is in series with the 45 volt source. So I know the total current and I know the current through R1. Now that I know the current through R1, I can find the voltage across R1. Just use Ohm's Law. And make sure that you label your picture with each voltage as you find it. You're going to need those voltages later. So now that we've worked our way all the way to the left, we're now going to reverse direction and go back to the right and start solving for all the other resistors that we collapsed before. So I'm going to now reverse the picture. I removed RZ. Remember, RZ was the combination of R2 and RY. I've removed it now. I've gone back to this step. And I know now that the current going into this node is the current through R1, 8.84 milliamps. I can now do a current divider to figure out the current through R2. I can also use KVL to find the current through R2. You can pick which way you want to do it. Current divider, KVL. In this case, if I do a loop, I'm going to have 8.84 volts plus the voltage for R2 has to be equal to 45 volts. Or another way to think about it is this voltage plus this voltage has to be 45 volts. So take the difference between these two to figure out VR2. Now that I know the voltage for R2, I can find the current. The nice thing about ladder networks is once you find one thing, either a current or a voltage, you can automatically go find the other thing. So I can use Ohm's Law to find the current through R2. Current through R2 has to be the voltage across divided by 8.2 kiloohms. So now I have my second current through R2. The next step is to use KCL to find the current going this way. I know how much current went in, and I know how much went out this way. So I can use KCL to figure out how much went the next way. 8.84 minus the 4.41 tells me I get 4.43 milliamps through this piece of the circuit, through RY. Now, let's remove RY. RY was the combination of R3 and RX. So see how I've removed RY and put R3 and RX back in. We just figured out how much current flows through here. So we now know the current through R3 because RY replaced R3. The current through RY has to be the current through R3, which means I can also find the voltage for R. Notice again, I'm adding the voltages with polarity to my diagram as I go along. For the next step, I'm now going to find the voltage for Rx. I know what Rx is, we've already calculated that. The current through Rx has to be the current through R3. These two things are in series. I'm going to find the voltage for Rx. Use Ohm's Law. The voltage for Rx has to be the current going through it, which is the current for I3, times its value, which we previously calculated. I could have also found the voltage for Rx by using KVL. The voltage here has to be equal to the sum of these two voltages because this makes a closed loop. So now I have the voltage for Rx. I'm going to remove Rx. So here's Rx. I'm going to remove Rx. Rx was the combination of R4 and Rw. The voltage across Rx is the voltage across what Rx replaced, which is these two resistors. Therefore, I now know the voltage for R4. The voltage for R4 has to be the same as the voltage for Rx. And if I know the voltage, I can go now find the current for R4 using Ohm's Law. There's my current for R4. Next, I can use KCL to find the current through Rw. I could also use Ohm's Law to find the current through Rw. I could take the voltage across Rw and divide by Rw to get the current through Rw. Or I can use KCL. You can pick either way, it doesn't matter. I know that the current going in here is the current from R3. I know that some goes this way, that's the current for R4, which means the rest had to go this way. That's how I get this equation here. So now that I know the current through Rw, let's remove Rw. What did Rw replace? Rw replaced R5 and R6. So I'm going to remove Rw and put R5 and R6 back. The current through Rw has to be the current through what it replaced. So the current through Rw is automatically the current for R5 and R6. Once I know that, I can find the voltage for R5 and R6. They happen to have the same voltage because they have the same resistance value and the same current. And there's my final label showing each voltage. Oh, I'm sorry, one more thing. The voltage at each node with respect to ground, for example, the voltage from point A to ground would be the voltage across R2. The voltage from point B to ground would be the voltage across R4. The voltage at point C to ground would be the voltage across R6. This is how we analyze a ladder network. There are a lot of steps involved. It can be very tedious. If you take it one step at a time and use your relationships, use your tools, you have all the tools you need to solve a circuit like this. You just have to know when and where to apply them. So as you analyze a ladder network, keep in mind you have to collapse typically from right to left first to find a total resistance and a total current. Then you're going to decollapse left to right and apply KCL, KVL, Ohm's Law, voltage divider, or a current divider in order to find each additional value as you work back to the right. Draw lots of pictures as you're doing this. Draw a picture for every step and label it very carefully. That will really help you to analyze a ladder network. The last topic in this video is a Wheatstone Bridge. An example of a Wheatstone Bridge is shown below. It has a configuration that's a diamond shape where you measure the voltage from points A to B. A balanced Wheatstone Bridge has an output voltage that's equal to 0. So a perfect Wheatstone Bridge would have a voltage that's equal to 0. Wheatstone bridges are used in medical sensors, scales, and precision measurements. When the bridge is unbalanced, the output voltage is not going to equal 0. The unbalanced bridge is used to measure physical quantities like mechanical strain, temperature, or pressure, and that's done using a transducer. The value of the parameter being measured can be determined by the amount that the bridge is unbalanced. So again, when a wheat bridge is unbalanced, the output voltage is not equal to 0. You can measure that output voltage and you can correlate it to a physical measurement like temperature or pressure. So all we're going to do is determine the value of Rx in the balanced wheat bridge shown below. Now this one is balanced, which means this voltage should be 0. And to do this, we basically just have to know a single relationship. In a Wheatstone bridge, Rx, which will always be here, is always going to be R2 divided by R4 times RV. And RV is what we call a variable resistor. You can change its resistance level. So if you were using this Wheatstone bridge to take a measurement, you would vary this resistance until you got an output voltage of 0. However much you had to vary the resistance tells you the measurement that you were trying to record. So in this case, the important information about a Wheatstone bridge is this relationship right here. Rx is R2 over R4 times RV. So you can figure out what Rx has to be by using this relationship here. Rx comes out to be 1800 ohms. And that's really all you need to know about Wheatstone bridges for now. Just know that this general relationship is used between all of the resistors in the bridge. And that's the end of this video.